Hello all, in this video we are going to discuss about AVL tree. Before we are entering into AVL tree, we should know about what is binary search tree. So binary search tree means the root node has some value. For example, take 20. So lesser than the 20 means 1 to 19 19 is called as the lesser value of 20. That values are placed as a left child of root node. And then greater than the 20 means 21 to 100. So example we have taken 100. So all values are greater only. So 21 to 100 that will be placed as a right child of the root node 20. So this is the property of binary search tree. The root node has some key value. Lesser than the key is placed as a left child. Greater than the key is placed as a right child. This is the concept of binary search tree that we have discussed detailedly in the previous video. Now we can enter into the AVL tree. So AVL tree is nothing but it's a self-balanced binary search tree or ordered binary search tree. Okay, here everything is same as binary search tree. Only extra condition here is the balancing condition. So here in AVL tree, it's a balanced binary search tree. So how we can check the balancing condition of the AVL tree? So that we will discuss detailedly in this session. So here, why it is named as AVL tree means the name of the inventor. So this tree will be invented by the persons Adelson, Belsky, and Landy. So that's why this will be named as AVL tree. Okay. So this is also called as self-balancing binary search tree. So these are the properties of AVL tree. It should be a binary search tree. The first property, it should be a binary search tree. And here we are going to find the balance factor for every node. So in whole tree we have to take in all node we have to check the balance factor. So here the balance factor is has three value. One is 1, -1 and 0. These are the three valid balance factor for the AVL tree. So the values are 0, 1 and -1. So these three are called as a balance factor. If the node contains any one of these balance factor means definitely the tree is a balanced one. Otherwise, if the tree is an imbalanced one, we have to make a tree as a balanced one. Uh, then only it will be called as an AVL tree. Okay. So next, how to find this balance factor? So to find this balance factor, we have formula. So balance factor is equal to height of the left subtree minus height of the right subtree. Okay. So in AVL tree, we have the three operations that is searching, insertion, deletion. So here the time complexity for all this operation it will take only order of log n time. So this is about the intro about the AVL tree. So it is a self-balanced binary search tree. Here we are for maintaining the balance factor for each and every node. If all the nodes should contain either the -1 or 0 or 1. So how to find this balance factor means balance factor is equal to height of the left subtree minus height of the right subtree. So this is called as balance factor. So next I will discuss. Yeah. So this is the sample, one example tree. Okay, this is a sample. So in this sample, so first we can find the balance factor for each and every node of the tree. So first let us take the leaf level. So first take the 12. So if okay, we need to find the balance factor of this 12 means first we have to find the height. Okay, left subtree height as well as right subtree height. Here for the 12 there is no left and right child. So it's a only node. This is called as a leaf node. So here the balance factor for this node is 0. Next, we have to take a 10. For this 10, we have to, to find the balance factor of this 10, we need to check the left subtree height as well as right subtree height of this 10. For the 10, there is no left subtree, so the height is 0. For the 10, the right subtree, the height is 1. So 0 minus 1 is -1. So this is the balance factor of node 10. Next, let us take 20. For this 20, so left subtree height is here the path height. So here the path height is the two edges are available 1 and this one is 2. So the left subtree height of the 20 is 2. The right subtree height of the 20 is 1. So 2 minus 1 is 1. So that's why here the balance factor is 1. Let us take 28, 38 and 48. These are all called as a leaf node. So there is no left and right children. So here definitely the value of the balance factor is 0 for all this leaf node. So next we will take a 30. So left subtree height is 1, right subtree is there is no right subtree. So 0, okay, here the left subtree height is 1. So 1 minus 0 is 1. For the 40, the left subtree height is also 1 and right subtree height is also 1. So 1 minus 1 is 0. For the 36 means here the height. Okay, here the height of the left subtree is 2 and then here the height of the right subtree also 2. So 2 minus 2 is 0 and let's take a 25. So there's a root node. The height of the balance factor for this root node is take a longest path in the left hand side, likewise take a longest path in the right hand side. Here the height is 3. The 3 number of edges are there from 25 to 12. So here 1 and 2 and 3. So these are the 3 edges. And next we can take a right subtree of the 25. So here also the 3 edges are available from 25 to 48. So first edge the 25 to 36 and next edge is 36 to 40 and next edge is 40 to 48. So here also 3 edges available. So the height is, yeah, wait a minute. Yeah. So here the height is left subtree height is 3 and right subtree height is also 3. So 3 minus 3 is 0. So this is a way to find the balance factor for every node of the tree. So once you found the balance factor, we have to check whether all the nodes contain the values of 0, minus 1 or plus 1. If all nodes are having the values of zeros, minus 1 and plus 1 means the tree is a balanced one, no issues. So it satisfies the property of AVL tree in case. Okay, so take this example, check whether this tree is a AVL tree or not. So here first we can take a balance factor for the 6. Here the left subtree height is 2 because the two edges are available. In right subtree height is 3 because the three edges are available. So 2 minus 3 is minus 1 for the 6. For the 4 also 1 and for the 1 is balance factor 0. Here for this 8 is the left subtree height is 1, right subtree height is 2. So 1 minus 2 is minus 1. 7 and 10, 12 are called as the leaf nodes. So here the balance factor is 0. For the 11, left and right is equal, so 0. So now all the nodes are contains the values of 0, 1 and minus 1. So this is called as AVL tree. Now take this example. Tell me whether this is the AVL tree or not. So in this example, the height of the left subtree of 6 is 1, 2, 1, 2, 3, 4. So here the left subtree height is 4 and right subtree height is 1 and 2. So 2, 4 minus 2 is 2. So the balance factor for the 6 is 2 and likewise here the 4 is 3 minus 1 is 2 and for this 8 is 0 and then others are also even this 1 also the balance factor is left subtree is 0 and then right subtree is 2, so 0 minus 2 is minus 2. So the 1, 4, 6, okay, these nodes are having a balance factor of minus 2 and plus 2. So now this is not an AVL tree because the valid balance factors are 0, minus 1 and plus 1. So here this 3 contains a balance factor of greater value 2. So this is not an AVL tree. So this is a base of AVL tree. So next we will discuss the operations of AVL tree. Already I said earlier. So there are three operations for the AVL tree. One is search operation. Next one is insertion operation. And third one is deletion operation. So all are same as the binary search tree that we have discussed detailedly in the previous session. But only minor difference here, every insertion, every single node insertion, you have to maintain the tree is balanced or not because AVL tree is ordered a binary search tree or it's a self-balanced binary search tree. So that is the only difference in the AVL tree and binary search tree insertion. So now we will check about the AVL tree operation. So these are the three operations: searching, insertion, and deletion. I will not get into more detail on search as well as deletion. So directly we can go to the insertion. So in insertion, after inserting some value, if the tree is not balanced, we have to make a tree as a balanced one. Okay, for that in AVL tree, we are going to follow the four type of rotation. Wait. Yeah, so these are the AVL tree rotations. So here why we are using this rotation means after the insertion that the tree is not balanced means if it is a imbalanced tree means we have to make a tree as a balanced one. For that we need a rotation to make a tree as a balanced one. So here the two type of rotation, single rotation, double rotation. In single rotation, further we have two cases, and double rotation also further we have two cases. That's why I told four type of rotations are there in the AVL tree. Let's see one by one with this notes. Yeah, wait a minute. Yeah. So here these are the four type of rotation. So LL case and then RR case and then LR case and then oral case. Left subtree of left child, right subtree of right child, and then left subtree of right child, right subtree of left child. So these are the four cases. In single rotation means LL or R. This is called a single rotation. Double rotation means L and R combination, R and L combination. So these are the four rotations of AVL tree. First, we will discuss the rotations one by one. Okay, first rotation is the RR rotation, right subtree of right child case. So just check with this example. Okay, so first we have even we can make a tree in the alphabets also. Here we have the alphabets A, B, C. As per the binary search tree property, A is a smaller value and B is a greater than the A. That's why the B is placed as the right of the A. And C is also greater than the B. That's why the C is placed as a right of the B. Okay, so we can construct the tree for the alphabets also. So you have to use, if you are using the alphabets means you can use a order of the alphabets. We have 26 alphabets. A is the number one letter and B is the second letter. Likewise, you have to check the order of the letter. Based on that, you have to follow the binary search tree property. If it is a number, you can easily identify which one is a greater number, which one is a lesser number. Based on that, you can insert. But here, if it is an alphabets, you can check with the order. Which one is the first letter, second letter, third letter, and up to 26 letter, you have to check the order of the alphabets. So in this example, we are going to discuss the RR rotation, right subtree of right child case. So already A, and then next B is inserted, then C is inserted. So now check the balance factor for this tree. So here the B balance factor is 1, C balance factor is 0, because C is a leaf node, the balance factor is 0 because there is no left and right tree. And for the B, there is no left subtree, but it has one right subtree. So the right subtree edge is 1. So 0 minus 1 is minus 1. So here in this A, there is no left subtree and right subtree 2. So 0 minus 2 is 2. So here, this will be a not a valid balance factor because A contains not a valid balance factor. So now this tree is called as a imbalanced one. This is a right unbalanced tree. Now, in this case, we have to make a tree as a balanced one. So, for that, we have to call a rotation. So, here this rotation type, first we have to identify this type of rotation is right subtree of right child case. So, A, right hand side, again the child also inserted in right subtree. So, this is a case of right hand side, right subtree of right child case. If it is RR case means we have to take a single rotation in a anti-clockwise direction. So here the which node we have to take and which node we have to make a rotation means the last inserted node. So here the B is a node. In this B node only the insertion has happened. So you have to take this B and then we have to tilt one portion in anti-clockwise direction. So we are just rotating a B in anti-clockwise direction one step. So now this is the tilting of B. So now B becomes a root node and A becomes a left and C becomes a right child of this B. So now check the balance factors. All are contains a zero value. So now it is a AVL tree. So this is the first rotation case, RR case. Likewise, we can take a LL case. Okay, so in this LL case, is a left subtree of left child case. The same example in this reverse. Okay, contrast in this right unbalanced. Here we are going to discuss the left unbalanced tree. So here C, B, A. C is a greater and B is the smallest and A is the smallest of B. Okay, so now this is unbalanced. Again, this is a case of left subtree of left child. See left hand side, and again the child A is placed in a left child as a left child. So this is LL case, left subtree of left child case. So in this case, we have to again make a tree as a balanced one. For that, we have to take a single rotation. Single rotation case name is LL case, left subtree of left child case. So for that here also you have to take which, okay, where the insertions happen. In this B node only the insertions happen. So we have to make a one rotation in clockwise direction for the B. So now B becomes the root node and A becomes a left subtree and C becomes a right subtree. So this is called as the left subtree of left child case. Okay. So these two are called as RR and LL is called as a single rotation. Now we can check with the LR rotation, left subtree of right rotation. Okay, so these cases called as double rotation case. So now for this double rotation case, we will take this condition. Okay, C is a root node. Then we have inserted the A, it is the smallest value. Then we are inserting the B. B is a greater than the A, so it will be placed as a right child for the A. So now this case, okay, here is a left subtree and right child happen. So this is called as LR case. So in this LR case means here the tree is not a balanced one because the balance factor for the C is a 2. So it is not a balanced tree. So to make this tree as a balanced one, again we have to take a rotation. Here this rotation case is LR case, left subtree of right child case. If it is LR means two rotation. For the two rotation means here the LR means the RR first followed by LL. So the two rotation, first we have to take a single rotation of RR followed by the single rotation of LL. So that's why this is called as the double rotation. Okay. First we are going to take a, okay, first RR case means anti-clockwise direction. Now here the B will be moved to the A position, one rotation, then B will be moved to the C position. That's why it is called as a double rotation case. The node will be moved to the first one position, then second at the C position. The two node movements will be happen here. That's why it is a double rotation. So now we are going to perform the RR case. LR case means RR followed by LL. So RR means the anti-clockwise direction of one rotation. So now the B becomes a root. So now the B becomes root means A should be a left of B. So now again we are going to take the LL case. So and clockwise direction one rotation. So now B becomes a root node. Okay, this is a case. Becomes a root node and then A is a left child and C is a right child. So this is called as LR case. LR case means you can take an example like a less than symbol. This is a structure for the double rotation. If it is a single rotation means LL and RR case, we can get a structure of slanting line case. Either this left hand side slanting or right hand side slanting, but for the double rotation case, you have to take a structure of less than symbol for the LR case. And then for oral case, we have to take a greater than symbol. So through that, you can understand which rotation we have to perform. So without any confusion, this is like a shortcut. Okay, this is tips for identifying the rotation. If it is a slanting insertion happen, that will be a single rotation definitely. So after the insertion happen, the structure of the tree looks like the greater the symbol or a less than symbol means definitely is a double rotation case. So now we have discussed the LR case. Next we will discuss the oral case. Okay, so in oral case means, okay, here the A is a root node and C is a greater, so it should be a right child for the A, and B is a smaller, so it is a left of the C. Again we have a structure of greater than symbol. So if it is in this case means definitely it's a double rotation case. So this is the right subtree, left child insertion happens, so this is called as oral case. So in this case, we have to perform the double rotation. Here the double rotations are first LL case and followed by RR case. So here LL means the one step clockwise. The B is moved to the C position with the one step clockwise. Now the tree becomes B is the root and C is the child. Again, we have to take a RR rotation. So in anti-clockwise direction, we have to tilt the tree. So now the B becomes a root and A becomes the child, left child, and C becomes a right child. So this is called as oral case. Okay, oral case means here is a double rotation case. Here we have to perform the LL rotation first, followed by the RR rotation. The two continuous single rotations are called as double rotation. So here also one tips in LR case means it's a less than symbol. So which two rotation we have to take means LR means it's end with the R. So first you have to take a RR rotation followed by LL. Likewise, oral case means it's end with the L. So LL first and followed by RR. So if RR case means we have to take a structure as greater than symbol. For LR case, we have to take a symbol as less than symbol. So this is a less than symbol for the LR case, and for oral case is a greater than symbol. So these are the four rotations of AVL tree. So totally we have four rotation, single rotation two cases, LL case, RR case. In double rotation two cases are LR case and then RL case. So why these rotations are used means to make a tree as a balanced one. Already the tree should be in an imbalanced position means that we can convert as a balanced one. So this is about AVL tree introductions and the four type of rotation. In the next session, we will discuss about the AVL tree construction with the one sample input. Thank you all.